Okay, looking at systems of nonlinear equations. We have the example x squared equals 4, x plus y equals 2. This is two equations in the unknowns x and y. How do we solve the system? Well, one way to solve it, just using common sense, is if x squared equals 4, well, we could conclude that x equals 2. It wouldn't be a particularly good conclusion, but it would lead us to something, and we'll see why it wasn't a good conclusion. It's not really a conclusion. But if x squared equals 4, we just say, okay, x equals 2. If x equals 2 and x plus y equals 2, then y better be equal to 0. So the ordered pair 2, 0 would be a solution. Okay? Well, I said that isn't a complete solution because x squared equals 4 has another solution. So we didn't have a conclusion by concluding that x equals 2. X could equal negative 2, in which case negative 2 plus y would equal 2, so that y would equal 4. So we get two solutions. X equals 2, y equals 0, x equals negative 2, y equals 4. Now, more formally, because we can't always just solve things in our head, what I just did is perfectly valid as long as you write out all the solutions to x squared equals 4, okay, which would be 2 and negative 2. You would immediately get the solution set. I'm going to do it a little differently. We'll solve the second equation for x to get x equals 2 minus y. We plug that into the first equation, we get 2 minus y quantity squared equals 4. So that 2 minus y equals plus or minus the square root of 4. Well then, square root of 4, of course, is 2. That 2 minus y equals 2 gives us y equals 0. And the other solution, 2 minus y equals negative square root of 4, would be 2 minus y equals negative 2, gives us y equals 4. Okay, well, if y equals 0, then x, which equals 2 minus y, would have to be 2. And if y equals 4, then x, which equals 2 minus y, would be 2 minus 4, or negative 2, so that we would have solution x equals 2, y equals 0, again the point 2, 0, and x equals negative 2, y equals 4, negative 2, 4. Just two ways to solve this simple equation. Okay, well, let's go to another system. Okay, system x squared equals y, x plus y equals 2. Okay? Now, yeah, I'm not going to make the comment. X squared equals y, x plus y equals 2. Once more, this system is just the same as this system, except it's x squared equals y. There's kind of an embarrassing reason why I chose this system here. I'm not going to mention it. If you were in class, you saw it. Again, we choose to solve the second equation for y, get y equals 2 minus x, so that we can plug that into the first equation. Now, if y is 2 minus x, that gives us x squared equals 2 minus x. And we recognize this as a quadratic equation. I hope we recognize this as a quadratic equation. We put it into standard quadratic form in preparation to use the quadratic formula if necessary. But in this case, we recognize that this expression is easily factored. X squared plus x minus 2 gives x plus 2 times x minus 1. That's equal to 0, meaning that x plus 2 is 0, or x minus 1 is 0. We conclude that x is negative 2 or x is 1. If we don't recognize that this thing is factorable, well, we plug into the quadratic formula. We're going to get the same values of x. If x is negative 2, then since y equals 2 minus x, 2 minus negative 2 being 4, y equals 4, so we have solution negative 2, 4. If x equals 1, plugging into y equals 2 minus x, we get y equals 1. So our solution set is negative 2, 4, this solution, or 1, 1, this solution. This corresponds to what we would get if we graph these two equations. X squared equals y gives us our standard y equals x squared parabola. X plus y equals 2 is a linear function with x-intercept 2 and y-intercept 2. So here's our linear function, 2 intercepts. There's a graph of our linear function. This graph intersects this graph. Unlike linear functions, if you have two quadratic functions or a linear function and a quadratic function, you can get two intersection points, you get two solutions. Okay, well, we estimate the solution here to be negative 2.24.5 from my not quite precise graph. And this one looks, there's no reason not to estimate this solution as 1, 1. We might estimate 1, 1.3 or 1.2 a little more honestly, but just slop it down as 1, 1, and just out of pure luck, 1, 1 does match this solution. Negative 2.24.5 is reasonably close to negative 2.4, and this confirms that this solution is in the right ballpark, so we probably did the algebra right, so this solution is pretty well confirmed. Of course, we can substitute negative 2.4 into this equation, and we see that we get 4 equals 4. We substitute it into this equation, and we see that we get 2 equals 2. We substitute 1, 1 into this equation, we get 1 equals 1. Substitute 1, 1 into this equation, we get 1, 1 and 1 is 2, something we always pretty well know. So we confirm our solutions. Okay. Well, that's two systems. I think I have, no, don't have anything on this side. Okay. Well, we have a couple more examples. Starting over here, we have a little more complicated expression up here that involves an x squared, and then an x and a y and a number, and a linear function here. Well, we can solve the second equation for y, getting y equals 1/3 x plus 4/3, if I did that correctly. And we can substitute into the first equation, and we get this quadratic. Now actually, I did that, so I'll just kind of point here. Here are the details. Solving the second equation, we get y equals negative x over 3 plus 4/3. Plugging that into the first equation, our y is going to be replaced by the negative x over 3 plus 4/3. We then multiply this equation, every term by 3, and we collect our terms. And if I'm correct, we get 3x squared plus 8x plus 15 equals 0. Well, here's a summary of that. Here's our 3x squared plus 8x plus 15 equals 0, an equation we can easily solve for x. Well, okay, we could go ahead and plug into the quadratic formula and go to all the trouble, but really first thing we want to check before we solve something using a quadratic formula is the discriminant, the b squared minus 4ac. In this case, b is 8, so b squared is 64. AC is 3 times 15, which is 45, so 4AC is 160. And we've got to subtract that 160 from the 64, giving us a negative. So whether you understand all those numbers or not, you can easily do it yourself. I didn't write them down, but you have a negative discriminant, so there's no real solution. Well, what does that look like if we graph it? Graphically, your first equation, which is, well, here, can be written as y equals negative x squared minus 3x plus 4. Just get all that stuff on the other side. There we have it. That's a parabola. Its axis of symmetry is that x equals negative 3 halves. its vertex, if I did it right in my head, then plugging in the coordinates of the axis of symmetry, I think is negative 11/4. That's going to give you a parabola with a vertex at negative 3/2, negative 11/4. And you have a negative coefficient of x, so it opens downward. The parabola is going to look like this. The line 2x plus 6y equals 8 has x-intercept when y equals 0, x is 4. So intercept would be 0, 4, which would be out here. If x is 0, y is 8/6, which is 4/3. So that's going to be like here. You're going to have a line with a pretty shallow negative slope that goes through intercepts on the positive x and the positive y axis. There's no way that line is going to intersect this parabola, which confirms the result that we got here. Here we say there's no real solution. Here we say there's no intersection. Okay, since every real solution is an intersection point, if we have no real solutions, we have, if we have no intersection points, we have no real solutions. Since every intersection point is, and I don't remember the way I just said it, since every intersection point is a solution, if we have no intersection points, we have no solutions. Since every solution corresponds to an intersection point, if we have no intersection points, we have no solutions. If we have no solutions, we have no intersection points. I'm still not sure I said that right, but there's a one-to-one correspondence between your solutions and your intersection points. Okay. Another example, it's kind of interesting, but way beyond what I'm likely to ask you. This system of equations, you can subtract the second equation here from the first, and you get this, which gives you y equals negative x squared plus 3x minus 16, but you haven't eliminated a variable. So we haven't eliminated a variable, if you can read that, like I wasn't able to. So this doesn't necessarily help. Although we could graph this, okay. The graph would be a parabola opening downward with the vertex at 3/2, and y-intercept, y value would be way down low, which would kind of mean, yeah, let's not worry about what it means. Don't want to explain it. Okay, well, didn't work. Okay, we didn't eliminate a variable, and it actually turns out to be pretty difficult to eliminate a variable here. Could be done, but only with a fair amount of trouble, more than we want to go to at this level. Okay, so a comment on this equation is, this is the equation of a circle. This is the equation of an ellipse. You can get the center and radius of the circle by completing the square on x here. And then you can complete the square on y here and get the center of your ellipse and put it into the standard form of an ellipse and get its semi-major and semi-minor axis. All stuff, well, at least the circle, you learn to do early in this course. The ellipse, you haven't, I don't think we've talked about ellipses and the graphs of ellipses, but your graphs might look something like this. And there might be two intersection points. I'm of the opinion, from calculations I did in my head, about where the center of the circle is. I believe at negative 3/2 is 0. And actually, I think I messed that up. I think the center should be at 3/2 0, which might well put the ellipse inside the circle. And anyhow, the estimates I made, the ellipse could be inside the circle, the ellipse and the circle could not intersect at all, and all kinds of things could happen. And that's interesting, but it's beyond the scope of the course. But being interesting, and since I made up the problem, I went ahead and talked about it. Okay, one other example. This system of equations. These are both quadratic functions of y. We can use our standard methods of graphing the quadratic functions. Each of these can be solved for y, which makes it easy to graph them. Okay? Now I didn't solve it, but if you solve this for y, you get y equals negative x squared minus 3x plus 7. You can figure out the vertex, the axis of symmetry in the vertex. And this one is easy to solve for y as well. You can figure out the axis of symmetry in the vertex. I did that in my head, got these two graphs. Okay? And according to these graphs, there should be two intersection points. If these graphs are right, turns out they're not that great, but one of them came out kind of close anyway. Okay, so to solve the system, you notice that we can eliminate y. We got a negative y here and a 3y here. So we take 3 times the first equation, add it to the second, we get this. Then we solve using the quadratic formula. And the square root of 340 is kind of close to 18. I'd say 18.3 maybe. But just ballparking it at 18, negative 10 plus 18 is 8. And the denominator is 10, so we get 8 over 10, or 0.8. Now I drew these intersection points before I got my solution to this equation. So I say here x is 0.8. Well, actually this intersection point is a little bit to the left of the axis, but 0.8 would be just a little bit to the right. And so this intersection point is kind of close to where you would expect it, at least on x. And then you plug 0.8 in here and you get something like something kind of close to 4. That makes a fair amount of sense. I thought I was doing pretty well at this point. But then we figure out the next intersection point. Well, negative 10 and negative 18 is negative 28, which is kind of close to 30, and 30 over 10 is 3, so we assume x equals 3. And said, okay, that's pretty close. And it looks like the x value ought to be pretty small, but if you plug x equals 3 into this equation, you get 9 here and 9 here, which is 18 minus 7, which is 11, when you add all this up. And you get y equals negative 11, which is going to be way down there. So this graph wasn't all that accurate. Somehow I kind of screwed that up, but I did it in my head, so I have an excuse. Okay. Nevertheless, it illustrates that you can eliminate y in a case like this. And also, you get two parabolas here. Anytime you've got two parabolas, you're going to be able to eliminate y. Okay. One other example that I guess I did on the back of this board is this one. Multiplied the first equation by xy to get this. Multiplied the second, or just took the second equation as it is, and I found that I could eliminate xy. Okay, well, I eliminated xy. I got this. I've got the second equation here. I actually didn't eliminate xy, okay. Multiplied the first equation by negative 3 in the second by 5 so that the xy coefficients would align. And I got this, and I got an equation that happened not to eliminate any of the other variables. Now I don't know why I've got a minus 6y here, because okay, well, here's a better solution. At this point, I realized that this is beyond the scope of the course, again, because the xy terms imply a rotation of the coordinate axes. And that's something we don't do until we learn a little bit of trigonometry in the second half of the course. So for this particular example, you can't go on with it. But there are examples in your homework where you encounter xy's, and what I really wanted to illustrate here is if you've got xy's in both equations, you probably want to eliminate them. And then proceed from that point. Okay, so good luck with the homework. I think you're going to be in good shape.